All right, so let's go ahead and talk about 5.1 vertex coloring and upper bounds. So for this section, we're going to finally introduce this idea of coloring our vertices, or in some other books, you might hear it just be called a labeling of our vertex. All right, so let's go ahead and start with some definitions as per usual. So the first definition I have for y'all today is, what is a K coloring? So a K coloring of some given graph, G, is actually a labeling, and we can define this labeling via a function from my vertex set to some set S, where the size of S is K. The labels of these vertices are what we call our colors, whereas if I'm looking at vertices of the same one color, these actually form what we call a color class. So we have a K coloring, colors, and then a color class. Another thing I want to mention is that a K coloring is called proper if whenever I take any pair of adjacent vertices, then they have a different color or a different label. So speaking of proper colorings, a graph is K colorable if it has a proper K coloring. So again, a proper K coloring means that for every pair of adjacent vertices, they have a different color. Whereas if I just have a regular K coloring that's not proper, I'm not really worried about having my adjacent vertices share or have different colors. So what happens if I am K colorable? Well, the chromatic number chi of G, or just chi, is the smallest value of K such that G is K colorable. In other words, the least number of colors that you need to give G a proper coloring. So in this section, we're going to talk about how do we color a graph. Can we find some quick upper bounds for the number of colors on the vertices of my graph? And one thing I want to note about this whole chapter is that whenever we discuss colorings, we're going to go ahead and assume that all of my graphs are simple. That is, they're loopless and they're finite. Furthermore, that we don't have any multi-edges. So what does a K coloring look like? What's a proper K coloring look like? And so on. So let's go ahead and look at this example here. So here I have the same graph, copy and paste it 3 times. And let's look at the far left graph. Notice for each of these vertices, rather than just a plain dot, I actually made them a little bit bigger so that we can see the colors. And just in case for just general accessibility, I also put a label on them with a number 1, 2, or 3. So for this graph on the far left, see that I have 2 colors. I have the color 1, and then I have the color 2, which I use this sort of striped pattern here. So if I look at this, this is a 2 coloring. I used 2 colors to color my vertices. However, if I look at these 2 vertices in particular, for example, these are adjacent, but they have the same color. Since these adjacent vertices have the same color, I do not have a proper 2 coloring. So this is an improper 2 coloring, or you can say a non-proper 2 coloring. There isn't really a formal term to say not proper. So again, this is not a proper 2 coloring because these 2 vertices are adjacent, but they still have the same color. So now let's move to this graph, this coloring in the middle. So you can see in this middle graph, I have 3 colors, 1, 2, and 3. 1 is this sort of solid blue color. 2 is this diagonal stripe, whereas 3 is this sort of brick pattern. So if I look at all of these vertices, for all of my colors, I don't have any pair of adjacent vertices sharing the same color. We can verify that very quickly just by, directly looking at it. So this is a 3 coloring, and in fact, it is a proper 3 coloring. Again, proper meaning that for any pair of adjacent vertices, I do not have the same color. So here I have a proper 3 coloring, but I can also do a little bit better than a 3 coloring. If I look on the graph on the far right over here, I use only 2 colors, so I know I am a 2 coloring. but am I a proper two coloring? So again, we can very quickly verify that whatever pair of vertices I look at, they have a different color. So this actually forms a proper two coloring. So I have an improper two coloring, a proper three coloring, and then a proper two coloring, like so. All right, so now that we have this example, let's go ahead and prove some propositions, maybe some theorems about colorings. So the first proposition here is let G be a simple graph and K be some natural number. If G is K colorable, meaning if I can use K colors on my graph and still get a proper coloring, then I should be able to also use K plus 1 colors to get a proper coloring. Furthermore, the chromatic number of G must be at most K. So here I have that same graph that we used earlier, in particular for my proper three coloring and proper two coloring. So on the right, I have my proper two coloring, meaning that G is two colorable for sure. By this proposition, this tells me that G is also three colorable. I could use three colors to get a proper coloring, just like what I've done right here. So why is this true in general? So if I look on my two coloring on the right, and if I just choose any vertex, I'm just going to use this middle one for convenience. If I change this middle color to a new color, that is a K plus 1 color, or in this case, the color 3, then I get the graph on the left. So I know if I just change a single vertex color into a new color, then it's still going to be proper because, well, before I was still proper, and whenever I add one new color to a single vertex, that shouldn't really change much for us. I just use one extra color. That's not going to cause me to have the same color on a pair of two vertices. So this is our idea of why the first part of this proposition is true. What about the second part? How do I know that the chromatic number is at most K if I have a K coloring that's proper? Well, remember, the chromatic number is essentially our best or most optimal amount of colors used. So for example, whenever I did this 3 coloring, for example, this told me that my chromatic number is at most 3. Or in fact, since I had a 2 coloring, at most 2. So if I give any coloring, let's say in this case the 2 coloring again, then either this 2 coloring is the least number of colors that I need, or maybe I can find a better option with 1 color. Well, as it turns out for this one color is not going to be sufficient for a proper coloring. So this is the idea for that second part. All right, so now that we proved a proposition, let's go ahead and introduce some more terms. I did say a couple of them a little bit early. So first, next definition, a graph G is K chromatic if the chromatic number is K. So this is just basically restating what we had earlier. K chromatic means chromatic number is some K value. Next, a proper K coloring of a K chromatic graph is called an optimal coloring. Well, if I have a K chromatic graph, that means I know it takes the minimum amount of colors needed to color that graph is K. So if I have a proper K coloring, then I have an optimal coloring. I don't want to say necessarily the best, but the best in terms of how many colors we need. Next is if I have a proper subgraph H of my graph G, and such that the chromatic number of my subgraph H is always strictly less than the chromatic number of G, then we say that G is color critical or K critical. So in other words, if I take any subgraph of my original graph G, then I actually need less colors, strictly less, not necessarily equal to. So we have these 3 quick definitions. So now let's go back to proving some propositions. The next proposition I have for y'all is for every graph on n vertices, so I have a graph with n vertices, however many that might be, then the chromatic number chi is always greater than or equal to omega of g. Remember that omega of g, this is my clique number. That is the largest clique subgraph or complete subgraph. And I have that chi is always greater than or equal to the number of vertices divided by alpha of g. And again, remember that alpha of g is my independence number. If I take all the independent sets of my graph G, alpha is the largest independent set. So why is this true? So just going through the proof very quickly for us. If I have a clique subgraph, that is a complete graph that is a subgraph of G, remember what does it mean to be a clique or a complete graph? That means in that subgraph, all of my vertices are connected to each other. So that means that if I try to do a coloring of that clique subgraph, each vertex has to have a distinct color. Thus, this actually automatically gives me that the chromatic number has to be at least omega of g. So here, for example, here I have K4, the 4 clique. Remember, in a 4 clique, we have 4 vertices, and all of these vertices are adjacent to each other by an edge. Since I have all of these edges connected to all of my other vertices, if I label this first one on the top left with the color 1, every other vertex has to have a different color than 1. So for example, I can label this one 2. These remaining 2 vertices cannot use 1 or 2, so I use 3 and then 4 respectively. So this proves that first part of my proposition here. But what about the second part? How do I know that chi has to be at least the number of vertices divided by the largest independent set size? So one thing that we want to note is that if I look at a graph, each color class in a proper coloring is actually an independent set of G. Remember, in a proper coloring, my colors are not adjacent to each other. So vertices of the same color are not adjacent. Or we can just say they're independent, in other words. Hence, if I take any color class, the biggest color class has to be bounded above by the largest independent set. In fact, you can almost think of these as almost interchangeably. I don't want to say exactly interchangeably. If I take any independent set, I can take all of those vertices and assign them the same color to form a color class. So whenever I take the number of vertices divided by the maximum size of my independent set, that is alpha of g, this should form an upper bound for the chromatic number. And that finishes our second part of this proposition. So we have this here. So this, in other words, we found some very quick lower bounds on my chromatic number. So if I can find lower bounds, can I find some upper bounds on the chromatic number? So I'm going to go ahead and introduce to y'all our new algorithm for this chapter. So fortunately for this algorithm, it's actually a little bit intuitive. So the next algorithm I have for y'all is the greedy coloring algorithm. And one thing I want you to know is notice that this is called a greedy algorithm. If you recall back a couple of chapters ago, greedy algorithms, these were these locally optimal, unsophisticated heuristics, meaning that they were best locally and may not be the best or most optimal or efficient solution. So this greedy coloring algorithm is actually going to give us a way to find a very quick, proper coloring. And hence, by finding a proper coloring, it gives me a quick upper bound for the chromatic number. So in this algorithm, our input is some uncolored graph G. So I have some graph G. I have not assigned any colors to any of my vertices yet. And as I said, my output or goal of this algorithm is giving me a proper coloring of the graph G, and consequently an upper bound on chi. So we have this here. So the idea behind this algorithm is that if I take any uncolored graph G, I'm going to assign colors to each vertex using the quote-unquote least available option. And I continue to use the least available option, and I don't use a new or higher ranked label or color unless I really need to. I'm trying to be greedy with my colors. I'm trying to use the least amount as possible. So how does this work? For initialization, I choose some arbitrary fixed vertex. And I'm going to label that first vertex with the color 1. So again, this can be any vertex of our choice. I can just start arbitrarily. From there, for each iteration, I can choose, again, any arbitrary uncolored vertex U. Again, this doesn't have to be any specific U. I can just choose any one of my choice. And I'm going to label U with the least available color while maintaining a proper coloring still. So if I choose a color for U, I just want to make sure that I do not have two vertices with the same color being adjacent. If I'm unable to use any of my original colors, then I add a new color and label U with that new color. And then if all vertices have in color, I can terminate. But if there's still an uncolored vertex, I repeat my iteration. So for termination, just so that we have all of our steps here, I terminate whenever all of my colors have a label. All of my vertices, sorry, have a color label. So this is our greedy coloring algorithm. So let's go ahead and see an example of this. So here I have some arbitrary graph that is uncolored or unlabeled. And I want to go ahead and try to figure out, can I find a quick upper bound on the chromatic number of this graph? So, applying the greedy coloring algorithm, I can find a proper coloring of some given size. So the greedy coloring algorithm states, let's start with some arbitrary start point. So I just chose this middle one, and I assign it the color 1. This is a result of iteration 1. So in fact, we're already done with iteration 1. Moving on to iteration 2, I'm going to go ahead and choose some arbitrary vertex that's uncolored. In this case, I'm going to choose this one. And then I'm going to give it a color, my least available color. So right now, the only colors I have is 1. But I cannot give it the color 1, otherwise I would not have a proper coloring. If this was the color 1, then I would have two vertices with the same color being adjacent. So I am forced to use a new color. In this case, let's use the color 2. This completes our second iteration. Now let's move into our third iteration. Again, let's choose some arbitrary uncolored vertex. To change it up, let's go ahead and choose this one here. Again, my choice of my new uncolored vertex is completely arbitrary. It does not have to be a neighbor of a colored vertex. It can be any one of my choice. So if I look at this vertex, my least available option, first off, I'm going to check, can I color this with the color 1? Well, let's see, if I color it with the option 1, I'm not breaking any of my proper coloring rules. So I assign it the color 1. And then I'm done with this iteration. Again, I'm choosing the least color. That's also why I did not choose the color 2. I want to choose the smallest number or the smallest color for each one. Now moving into iteration 4, again, I'm going to choose an arbitrary vertex. And then I'm going to ask, what can I color this with? First off, can I color this with the color 1? No, I can't, because this is already connected to this color 1. So I can't use the color 1 and move on to the color 2. Can I use the color 2? If I fill this with the color 2, it doesn't appear that I break any of my proper coloring rules. So I color it with the color 2. Finishing iteration 4. Next, we rinse and repeat. I choose some arbitrary vertex, and I try to color it with my least color. So I cannot color it with the color 1 because it's connected to a 1 color. I cannot choose the color 2 because it's connected to the color 2 already. So I am forced to add a new color. In this case, I will add the color 3, which looks like this purple brick pattern that I have here. So this is what I mean where we're checking the least colors, and I try to use my least colors until I have no choice but to add a new color. That completes iteration 5. Moving from there, again, I'm going to arbitrarily choose one of my other vertices. I can look at this one over here. And once again, I'm going to go down my list from least to greatest. For the color 1, I'm not allowed to use the color 1 because I'm already connected to 1. For the color 2, I cannot use the color 2 because I'm connected to this vertex up here. What about the color 3? Let's see, it looks like I'm not connected to the color 3, so let's assign it the color 3. That is, 3 was our least available option. So I have this here, completing iteration 6. And now I look at my last vertex here, and I go down my list, starting with the color 1. Am I allowed to use the color 1? Let's see, I'm not connected to any vertex of color 1 directly. So, in fact, I can use the color 1. So, just by observing my colors here, I have a proper coloring, or if I want to be exact, a proper 3 coloring. I used 3 colors. Since I have a proper 3 coloring, I could say that my graph G is 3 colorable. Furthermore, this algorithm also tells me since I am 3 colorable, then my chromatic number chi is at most 3. So we have at most 3 here. And in fact, if you want to take this a step further, I don't have this on the slide, we can actually prove that this chromatic number of this graph will actually be equal to 3. How can I prove that this chromatic number is actually exactly 3? Not just less than or equal to 3, but equal to 3. So one quick way that I would think of this is, remember that proposition we had earlier. If I know the click number of my graph, I can find a lower bound for chi. So if I look at this graph, notice that I have a 3-click subgraph. If I look at this top triangle, since I have a 3-click subgraph, that means my click number is 3, and I don't have a K4 subgraph. Well, since my click number is 3, remember that chi has to be bounded below by the click number, or omega. So that means chi is bounded between 3 and 3, implying that chi is actually exactly equal to 3. So a quick, nice way that we can get some bounds for this. So that was the greedy coloring algorithm. But I do want to put a quick disclaimer on this greedy coloring algorithm. It does not necessarily give us the most optimal proper coloring. In that case, it did turn out that we had an optimal proper coloring, but that's not always necessarily true. The goal of the greedy coloring algorithm is not necessarily finding the most optimal solution, but rather gives us a quick upper bound on the chromatic number. So we can see that before, if I go back a slide, for example, here I had 1, 2, 3, 4, 5, 6, 7 vertices, meaning that my algorithm had 7 iterations. Generally speaking, if I take any general graph, finding the exact value of my chromatic number is actually an NP hard problem, meaning that it's really hard to find it, very informally speaking, hard to find in polynomial time. So we have some notes about the greedy coloring algorithm. A little bit of an intuitive algorithm because we're just saying what's the least color that we can use before we are forced to use a new color. So from there, just some other short notes that I want to include. This next proposition, some more upper bounds. Chi is bounded above by the maximum degree plus 1, which we also know is bounded above by the number of vertices. So this second inequality, delta plus 1 is less than or equal than the number of vertices. This is already something that we are very familiar with. The number of vertices, the degree should be bounded above by the number of vertices. So very quickly, for this proof idea, I'm going to prove this first inequality, proving that chi is at most the maximum degree plus 1. So very roughly sketching the proof idea. So if I have some graph G, let me choose a vertex V of maximum degree. That is, the degree of V is equal to the maximum degree of G. We know that such a vertex must exist, otherwise our maximum degree would be something different. So if I were to look at that vertex V of maximum degree, let's say it looks something like this. Let's say, just for the sake of our example or proof, we have a vertex V with 1, 2, 3, 4, 5 neighbors. So what we're going to do here is that for V, let's assign it the color 0. I know usually we start with the color 1, but for the sake of making our proof a little bit cleaner in the writing, let's start off with the color 0. So if I start with the color 0, one thing I could do is that for each neighbor that I have, let's assign each one of them a different color. That is, for example, I can assign it the colors 1, 2, 3, 4, and 5. So by assigning each neighbor a different color, regardless on whether these two, for example, these two top vertices are adjacent or not, I'm still going to have a proper coloring of these vertices. And look, notice how many colors did I use. In this case, if my maximum degree is 5, I have 1, 2, 3, 4, 5 plus 1 colors being used to form a proper coloring of this subgraph. So I use delta of G plus 1 colors. So since my choice of V is arbitrary, this applies for any of my vertices, and this also applies for vertices of less degree, then I can use the same idea for each individual vertex. Hence, every proper coloring of my graph G, whatever it may be, must use at most delta of G plus 1 colors. Again, this is because my choice of V is arbitrary. So we have this proposition done. So the last theorem I want to show y'all for today is actually a named theorem. And it's actually a very big result in graph colorings. We're not actually going to go ahead and prove it, mainly because of the length of the proof, and it is a tad difficult to understand, especially at the undergrad level that we're looking at. But we're going to go ahead and introduce this. Theorem 5.1.2, and it's called Brooks' theorem. If I have a connected graph that is not a complete graph, nor an odd cycle, so it's not a KN, nor is it just an odd cycle, so a cycle with an odd number of vertices, then we actually have that the chromatic number is actually bounded above by exactly the maximum degree. So not just the maximum degree plus 1, but the maximum degree. So we have this here. All right, so this is Brooks' theorem. As I mentioned, this is a major result in graph colorings. If you are interested in looking in the proof, I did include it in the notes. There are also many other results that you could look into through any of our reference textbooks if you're particularly interested in vertex colorings. But besides that, that's all for this video.